Well, welcome back to our morning session. Now, Arkaitz, the floor is yours for lecture.
Thank you, Juan. Okay, welcome back, everybody. See, not many of you escaped, so wasn't that bad. So this is the very last lecture. So first couple lectures were like introduction to particles, the ones that I care about the most, mesons. We haven't talked about variance. And then we've been playing with things that we define with the quantum numbers, like these amplitudes, and I introduce you a customary way of describing. Now we're gonna go, I'm gonna up the notch a little. We're gonna go into the fancy analysis. What is the best of the best that we can do for these scattering processes? Can we get fully model independent results for these amplitudes? Can we get something that is once and for all, and we don't have to fight about using this or that model to describe the data? We're going to take a look at the light scalars. So I introduced them on Wednesday, and the idea is very simple. We have these knowledge motivated by the quark model. We have all the symmetries, right? The symmetries. And so if we have SU3, then we are going to have 9 states, 8 plus 1, octet plus singlet. Naively, if I knew nothing about particle physics, and then you introduce me the light scalars, I'd say this must be the simplest case. So we introduce the pseudo-scalar mesons, and then these arise as a result of the scattering of the pseudo-scalar mesons. So these are like the vectors, like the omega, the rho, the phi, only they don't have angular momentum, they don't have a spin. So if I ask you which one is going to be simpler, something with a spin or something without spin, you're going to say, oh, something without spin, right? These guys. Well, turns out they don't look anything like the shapes that we like, the Ribbinger shapes that we like. And their compositeness is also something that hasn't been answered for many years. We only have partial model-dependent answers, but we don't really know if they are tetrachords. We think that they might be more molecules. And there are some people that think some of these states might have some global components. So let's see how we describe, how do we go from errors this large for the parameters to something much more precise. So first things first, you want to describe a state. You want to tell me what this is made of. You want to understand QCD. Well, you gotta describe it with precision. Otherwise, we are not gonna go far from that, right? Well, turns out this is the past error value for the kappa state. So yeah, not very precise. This is what the PDG said about this state back in the day, 1967, where it was compared to some cool things like the Loch Ness Monster and the Abominable Snowman. And well, again, this is not needed. It's over there, you can see it. And so we're going to explain how to go from this to that. Okay? Now, not only that, we can also determine things like this scattering length that we were playing with before. And there is some controversy there between lattice QCD driven values and our dispersive results. So we will say just a few words on that. The big problem, because there are two big problems with these scattering processes. So first big problem, all these light scalars depend on many complicated analytic structures. So I introduced to you this branch cut thing that happens when data exists. This is basically the threshold of the reaction for pi k scattering, and this is the real axis. And this is the physical region where data exists, right? So you feed data here, and then you want to get poles. The k star, one of the vectors, lives very close to the data. So, okay, this is a short trip. You can do it by walking distance, and it's fine. You get a k star. And now the kappa lives here. It's very far from data. Data is to the right of kappa. But to the left, there is a whole lot of things that we cannot describe with data because they are not in the physical region, but they are there. We can prove it analytically. So if you want to describe some of these states, well, you are not only going to need data, but you're also going to need the low energy expansion region, which is below threshold, something that is called the Adler field that we won't describe, you might know about, and what we call the left-hand cut, which is very complicated, right? It has a circle and everything, and this complicated structure. Otherwise, you won't be able to go to this pole with precision. If you do use models for this, that don't account for all these low energy regions, then you will end up with a spread issue. And this was debated for 50 years from the sigma. So, it's not very good. And this is something that we also see on the lattice nodes, because the lighter the pion mass, the more these things are relevant. Because in lattice QCD, the masses of the pions are usually, well, back in the day, they were very heavy. So this thing is pushed to the right. But let's say this thing and this thing are farther apart, okay? But the lighter the pion mass, the closer these two are. So the more relevant it becomes. And this produces slabs and separates. This is just one of the problems, which is the analyticity problem. There is another problem, which is the experimental problem. And if you remember that all these measures decay, not under the strong force, but they do decay. So they leave for some meters. That's fine, we can play with one of them, but playing with two of them is complicated. Because if you have a big accelerator and you start with two beams that are farther apart, at the end of the day, what you collide is vacuum. So you miss them, and you no longer have two measurements. And this means that data is not data. Data has to be modeled from indirect measurements. Like, for example, this thing. So you have one measure beam that you can play with, just one, and then you make it collide a target. In this case, a prototype. But you can assume some point in some kinematical region that this thing is mediated by a pion as a virtual particle, okay? This is not a real particle, it's a virtual particle. If you have a good model and the kinematics are perfect, okay, it's not terrible, but this is still a model reaction. So data is not data. And this ends up producing errors this large in the data. And some systematics are neglected because we do not understand them. So yeah, we have to be proactive here. So the solution is this. The solution is to invoke all these first principles. You've been introduced to unitary analysis in the previous lecture, and we're going to speak now about crossing, and how the three of them together can give us the right answer in this reaction, and so on. Okay, so what is crossing? Again, have these states that are influenced by the data on the right-hand cut and something that is called an effect. Crossing is the relation between particles and antiparticles. So we are going to cross a particle and antiparticle. In case of pi to pi, right? The antiparticle of a pion is a pion cell. So yes, they are related. So if you cross pi to pi, you get again pi to pi. And there must be a mathematical relation. This is a mathematical relation. We can define one amplitude, one analytic amplitude, and unitary amplitude, with respect to unitary, that describes all possible process depending on its variables, its one understand variables S, T, and U. So let's take a deeper look. This is what we call the direct channel. The data lives in the direct channel, what we can play with in the physical mode. And this is going to be called the cross channel. This is going to be produced by antiparticles. Okay? So as I said, we have one single amplitude that describes all these processes. I'm not going to prove that. It's not trivial. But we can take a look at what I mean by that. So let's say that I have one process, 1, 2, 2, 3, 4. So pi. And this process is above the S channel threshold level. So pions are interacting. It's in the physical level. This is the S channel process. 1, 2, 2, 3, 4. Fine. Let's say that I have one anti-3 to anti-2, 4. So pi to pi. But now the energy that is greater than the threshold is the T channel energy. This can be plotted like this. One anti-3 to anti-2, 4. Okay? This is another reaction, but they must be related through the variables. The third one is 1 anti-4 going to 3 anti-2. So now pi to pi. Yes, that another variable that drives everything now is U. And this is depicted in this. 1 anti-4 to 3 anti-2. So yes, we have 3 amplitudes, right, for this process, permutations. And the 3 of them, are physically these regions. Well, let's say that I put some conditionals, and I call this capital T, the combination of these 3, with some conditions. And in the middle, it's going to be something that goes analytically from one to the other. So we analytically continue this T, not only in these regions, but also outside those regions, to describe the full S, T, and U variables in the dimensional description. This is the whole connection. And so this is what we want. This is called the Mandel-Stahl hypothesis. Okay, or hypothesis, because there is no strong mathematical proof. You can get some decent skeleton expansion and description of this. I can point you to the book if you want. It's not true. Now, what are we going to do with this? So we are going to build here our own dispersion relation. I don't know if you have ever heard about dispersion relations, but they exist everywhere, and you have actually played with them. You want to solve a harmonic oscillator, and then you introduce a random force in the harmonic oscillator. You're going to solve a dispersion. Want to play with optics, the whole line propagates over different mediums. We're going to play with dispersion relations. Want to solve quantum mechanics and some non-ordinary potentials. You're going to play with dispersion relations, and the same in quantum field theory. Okay. But yes, we know what's the analytic structure of the amplitude. Let's simplify. You remember that we had some complicated circular left-hand cut and some simple right-hand cut. So let's start with a capital P function that has a very simple structure, much simpler than the puzzle. It's just straight lines to the right and to the left. Okay? Because it has cuts here. These cuts, remember, are the discontinuity jump of the produced by the imaginary parts, right? So we can go below and above them and have a path like this. And now the amplitude is analytic inside because we proved analyticity. So we can invoke the Cauchy theorem. You probably have played with it. Fine. So we have everything, and now we're going to assume that this path, that is going to go to infinity, is negligible because my amplitude decays very quickly. If not, we have to do something. But let's start by assuming that, okay? This part is going to be negligible, and it means that we are going to have to care about the continuous paths. So it's going to look like this. This is going to be where data is, and this is the left hand. Wait, I'm going too fast. Why an imaginary path? Went from T to an imaginary path. Well, you can see it here. Let's get this right path. You have an integral that runs below the cut in the negative direction, and then a part that goes along the cut on the positive direction, plus a epsilon. So this is basically T of S prime plus a epsilon. S prime because I'm going to integrate on it, okay? That's why I'm using the prime variables. Minus E of S prime minus I epsilon, because it goes in the negative direction. And we proved this in the previous lecture. This 2i times the imaginary part on S prime plus H. We just proved. So yeah, imaginary part. This 2i is going to cancel the 2i in the denominator of the Cauchy theorem, and then we just recover that 1 over 2. What is the analytic formula, the right formula for this left hand? Well, let's look something like that. Now, let's simplify everything. Just pi pi, same mass. Pi pi to pi pi, same mass, or m pi squared. Okay? Just to calculate our first dispersion relation explicitly. So this is how the right cut red looks like, or data is in. Now we are defining the plus I epsilon on top of it. Okay, it's a limit on top of it. And this is where the left hand cut blue looks like. And we define the plus, we define a minus I epsilon below. This is convention, but I'm defining it that way to make things simple with signs. Now, the problem is data lives in here, but there is nothing over there. So we know nothing about that integral. We cannot calculate it. So let's do magic. Let's relate that cut to the right hand cut by using crossing. Now you'll see why so well. First, we're going to change the variables in this integral from S prime to something like this. As you do the algebra, you recover this expression. Now, this U prime is a dummy variable, right? I could call it U prime, I could call it L or C, whatever. It's just integrated, and we know what this is. Now, this integral looks like a right hand cut. So we went from something on the right hand cut plus something on the left hand cut to something on the right hand cut, yes, just on the right hand, right? Okay, we still have this weird thing. Now, remember that the three Mandel-Stahl variables are related, because ST and U give us a relation, right? Have you proved it? It was homework. Now, the idea is I am explicitly writing the third variable here, even though I usually don't, because we don't need it. Just to do the last relation. The last relation is to involve crossing. Crossing basically is going to tell us how the amplitude looks on this S and U and relate it mathematically with U, T, and S. You can also do it with T, S, and U. That's no problem. You just have different matrices here that makes everything. And those matrices you can calculate algebraically. They are basically transformation between Klotz-Gordon coefficients. So matrices that relate different Klotz-Gordon coefficients. Okay? Not very complicated. So this was our formula. And now this term in here is just going to be rotated from S and U to U and S. Remember that U prime now is a dummy variable. So I can very well call it just S prime. So S prime, S prime. And when I rotate U prime to this side, S prime again. And that is the final formula. Yep.
If we wanted to consider additional possible final states, would we then?
We'll go into that. But so the idea is that in an experiment, you can always tell me which final state you want, right? So this is pi pi going to pi pi. There will be other final states, right? But this formula still holds because it's pi pi to pi pi. Now, the channels will be here, okay? The elasticity for this link to other channels will be included here. We will go through that.
So then does this refer to components of the T matrix, which it corresponds to all possible decays?
No, so this is only pi pi to pi pi.
Okay.
So this is will be just the entry pi pi to pi pi.
Thank you.
Not in general language. So this will be just one entry. Okay, everything clear to this point? So what we did at the end of the day is we have an integral equation that is written just in terms of data. Now we can solve this, right? We have data, we can get this, and then we can calculate this with the integral equation. And this is what we are going to do. Now, the structure for a parser for these little t's is a bit more complicated, more cumbersome, not more complicated. Because you know what's the algorithm, what you want to do. It's not impossible. Problem is, we have this circular graph for the parsers. So everything is mixed in a weirder way, and the formulas are longer, but the same. The algorithm is something else. So you can get an integral equation that only depends on it. What is the path? The path towards a model-independent analysis. The path toward model-independent analysis is to impose the three Smalls principles in this reaction: unitarity, and analyticity that we already knew about, and finally crossing. When you work the three of them, you can get integral equations like this. Okay? So what we have to do, this is our recipe. First, we have to use all the data available, because as I said, data is not perfect. We want to be as close to perfection as possible. So we get the data, we feed the little this, the parse waves, and then with that we recover the amplitude. The second one will be what? Some data we know is obviously grown. Sorry to say, but some data has some systematic uncertainties that are not very well understood, and some others have like large uncertainties. So you might as well not use it because it doesn't tell you anything. Remember, some of these experiments are very old. So you can prune, and then you have to feed the data. The third one is obtain your favorite dispersion relations. This is the simplest one that you can get, and you can go to something way more elaborate. And the final one is green and red. So feed to the data and dispersive output, so solution of the integral equation, must be compatible. Because if they are not, then you are violating crossing. So you no longer describe the three first principles, right? So let's go through it. We are going to play with pi k scattering, which is my favorite chunk. For pi k scattering, instead of pi pi, the equations are more complicated. So in order to simplify, I'm going to just put t for the Mandelstam variables, right? The one that is here, equal to 0. So it's no longer a variable, it's just a variable. Second thing is, in the literature for that, we decided for no good reason, I think, use F, capital F instead of capital T. So now I'm going to call it F instead of T, and little f instead of little t. Okay? We can describe little f as we did before. So if you have data on pi k, you can use this formula in the elastic region with an expansion like the ones we were discussing. And in the elastic region, we can do all of this, but we can still describe it. And what we care about is this channel, the channel that goes from pi k to the kappa resonance back to pi k. Does anybody know what is the isospin of that channel? It's 1/2. So what is this thing? I mean, we forgot about isospins, but they are relevant. We have pi k scattering. So which are the isospins? Well, I mean, they are here, so you can read them. But yes, what is the isospin of a pi? What? And the isospin of a kn? 1/2. So what is the possible combinations? 1/2 and 3/2. Okay. So this means that we have two different amplitudes. In blue, I can, I can rotate the bases. I can do some mixes. That's no problem. The idea is that I'm choosing this definition of my amplitudes, which is a combination of isospins, because they're very convenient. And they are related to the green amplitudes, capital G, sorry. The green functions is crossing. Remember, crossing is going to relate, for example, 1, 2, 3, 4 to 1 anti-3, 1 anti-2, 4. What is that? That is pi to k bar, right? So the cross channel of pi k to pi k is either pi k to pi k or pi to k bar. So we want to describe everything, we need to fit the two channels. Fine, we can do that. These are the definition of the partial waves. You give me data here, I describe the amplitudes, and then my dispersive result. So this is how data looks like. Okay, use all possible data. As you see, it's messy. And as I said, some of this data are wrong. We can prove it that it's wrong. Otherwise, we will use as much data as possible. Some other data, you include it in the fit, but they have huge uncertainties. So at the end of the day, it's like you didn't include it, right? How do you fit it? By minimizing the likelihood, which is a chi-square fit, right? Which has the errors on the denominator. So if the error is huge, the weight of that data point is 0 basically to our likelihood. Most of it, all this data was produced in the 80s. This is still the best data we have of today. And we will run a new experiment at Jefferson Lab in a few years that is going to measure this, hopefully with more precision and less systematics. Now let's prune it and fit it. So I'm showing you the most precise data for some scalars, some different isospins. The important thing here is that all those fits that you see here were done with something this simple. I promise that it's simple yet powerful, and indeed you see some explicit fits that we did with that formula. So it works. And so we have now our fits. We have our partial wave and our amplitudes. And our idea is that we have to choose our dispersion relations. They are not that simple for pi k. And as I said, they are much more complicated for partial waves. But the thing is this. So let's say that you start from a capital F, and then you project to a little f, and you get your dispersion relation. Now, these k functions and capital G functions that I have in the integrants are algebraic. We know the answer algebraically. They are not trivial, but we know we don't need to write it. These are the fits to the data. And the same for the cross channel. There's a complicated dispersion relation, but in colors, green is pi to k bar, blue is pi k to pi k. So you see, if you fit the data, you can get this dispersive answer. So you have a system of integral equations, and you can solve that if you have a description of your data. Now, you can prove that this result, this dispersive result, is unique if you do it properly. So we impose the 3 first principles, we get some data, and we constrain the 3 first principles, and at the end of the day, the result is unique. And this is what we consider a model-independent description of the parcels. Okay? If you were to use a different model, quote unquote, to describe the data, and you impose dispersion relations, you will always end up with the same result because it's unique. So it doesn't really matter which model do you use to describe the partial waves. If you describe the data and you do this, then at the end of the day, the result is just one. This is why we call model dependent. So the problem is we have to make the input and output compatible, and they are not by definition. So you feed the data, you calculate the integral equation, and then you look at the 2 of them, and you are like, oh, these curves must be identical. But they are far from identical. So these are the left parts. The 3 different colors mean 3 different integral equations for each partial wave that we are agreeing about in this plot. And you see The black line, the continuous black line, is the fit. They are definitely not compatible with an straight line. So we are violating something. In this case, we are violating what is called crossing. And we have to somehow make them compatible, because otherwise we don't have a model independent result. But this is evidentionistic. If I was to describe the data with different models, we will get different answers. So it's model dependent. But we can impose them. We know how to. The idea is just to vary the fits to the data a little bit. So we vary the fits to the data a little bit, so they still describe the data, roughly speaking. And then we can recover something where everything is perfectly compatible with the uncertainties. You can see the new fits to the data to the right with the gray bands, uncertainty bands. So it's still perfect. I mean, the chi-square is like 1.5, something like that on average, something very close to perfection. But we are describing all the first principles. And so no matter which model we choose to parameterize this data, we end up with the same solution. So finally, we got our full recipe. So we got our dish, and we did all these steps to get it. Now that we have it, we can calculate stuff. So we not only have model-independent descriptions of the amplitudes, we can calculate observables in here. Like for example, the scattering lengths. The scattering lengths, as I said, are very relevant. Some of you might work at some point or already working on chiral perturbation theory on lattice QCD at low energy scales. And so these scattering lengths are crucial to our understanding of the calcimetry breaking pattern and how chiral perturbation theory works. So the idea is, if you calculate this with dispersion ratios with a model-independent result, then you get these blue values. Then you have this purple band, which is in the background, this green band on top of the purple one, which are all coinciding to this same region, which are different dispersive calculations of these scattering lengths that we did. So this is what we consider a model-independent result with a good assessment of the uncertainty. Now, look at these three green dots in here. Right. They are clearly incompatible, right? Those are lattice QCD-driven results. We know more or less why they are incompatible, but the idea is that by doing calculations like this, you can answer questions that are debated for many years otherwise. This was debated for many years, and the kappa resonance has been debated for over 50 years. And the good thing is, by doing these dispersive approaches, we went from an error that looks like this, and from the PDG not accepting the kappa resonance in the booklet, to an error that looks like that, at least in our determination. Now, the PDG will probably put new bigger errors to have a conservative estimate, but this is what we predict. And the idea is that it's not only a model-independent result, but to the point that we included all the systematics that we knew about, otherwise we should have propagated more errors. We think that we did a good job, that we did. This is slightly larger than that. But the second thing is that it's very precise, right? Many quote-unquote models trying to describe this state are less precise than this result. And you should never just pick one model, because usually models are very deviated from the true solution. In particular for these states that are very complicated. So, this is not the only application to a scattering system that includes dispersion relations. This is just one of many. This is the one that we did recently, like less than 2 years ago. But you have others for pi in the past, which solved the same kind of troublesome case, which was the sigma instead of the kappa resonance. How precise the sigma is. And this is crucial because the sigma, for example, enters in many other possible reactions. And pi is one of the sets that populates the most final sets in accelerators. So if you don't solve it, then you cannot move forward. We also have answers for pyronucleon, the dispersion relations, and this relates to the pyronucleon sigma term, which is an observable, which is crucial to, for example, searches for dark matter, and also explains to you how does the mass of the nucleon depend on the mass of the strange form, for example. And we even have dispersive solutions for E plus E minus, which is a way of calculating contributions to the hadron vacuum polarization. And when you hear in the newspaper or wherever, that there is a 4.2 sigma deviation between the theoretical expectations and the experimental prediction, that theoretical prediction was calculated through the dispersive solution of E plus E minus. Okay? So it's not exactly what we did here, but very similar approach. That is what is driving these results and this tension. So if you ever claim to be above the 5 sigmas and there is beyond standard model physics, then what you have to do is take a look at these dispersive results. So pretty much what we did here. So well, did you like it? Join us. We have 2 collaborations in Jefferson Lab that work on spectroscopy and this amplitude analysis. And so I'm going to introduce to you the wall of JPAC physics, the Joint Physics Analysis Center. If you want to work with us, we're going to be taking a look at all the possible hybrids. Interesting. We have a measurement from Best Street that claims to have found the partner of the pi one that we've been discussing today. But hey, there should be 2 hybrids, not 1. What happened here? One of them disappeared. Now take a look at it. You want to do XYZ exotics? We might be able to answer those in a few years experimentally at Jefferson. If we do the upgrade, we will measure production of those XYZ exotics we get. Also in the EIC program, when the EIC is built. We want to say something about machine learning applied to exotics. We are working on that. We have results for pentacore searches, tetracore searches. But we want to develop 3-body formalism that we need to use now for more complicated reactions than just 2 to 2, right? And you wonder, why did I spend a few hours just talking about 2 to 2? You can have an infinite amount of particles in the final state. Yeah, and many others. You want to work on lattice QCD with us? Well, we're working on lots of projects. For example, somebody could ask, and then I should answer. What do we want to do at the end of the day? We get these states, we calculate the masses, and we put them in a table. Is this all we want? No, we want to understand what they are made of, right? So we want to see inside those states. Well, even use some photons to see something. So we can do that on the lattice nowadays. We have many possible reactions that we can study. If you have, for example, pi gamma by pi. Want to see what some of these F knots and A knots are made of? What is their flavor content? We can do that. If you want to know the charge radius, you can insert a photon now inside a resonance and tell me what the charge radius is. Maybe one day we can insert this. What is this? Which current is this? This is a Higgs. This is a scalar current. And you answer what is the mass radius of a resonance? Unfortunately, not yet. Hopefully. And we can only do other reactions and calculate every exotics. So yeah, if you like it, of course.
Questions for Arkaitz?
Is there any additional physics contained in subtraction terms when you relate, say, like the real and imaginary parts of these distributions that you're calculating?
Good one. Very good question. And, so, for example, here.
Yeah, exactly.
So what Andrew?
Yes.
So what Andrew is asking me, and for everybody, is if there is some physics inside terms like this. I think is this the question?
Yeah, I think so.
So I didn't go through this, of course. This is called a subtracted dispersion function. This is different from the ones we were playing with before. We looked at that because you don't have subtraction term. So we introduce a subtraction and a dispersion relation when the asymptotic limit of these amplitudes doesn't go to 0 as fast as it should to neglect this certain point. Doesn't, then we can suppress, over an extra power of S prime by introducing a subtraction. You can put as many terms as you want. You can put 10, 100, if you needed them to be. You don't need them to be. There are theorems that tell you that, roughly speaking, 2 subtractions are always more than necessary for all these reactions. But in principle, you could put as many as well. When you put a subtraction, so when you want an extra order of S prime minus something in the denominator, you're going to recover an amplitude like this one that shows up outside the integral. And this is evaluated at a point. So in a sense, it can be considered as some rule for the amplitude. So in this sense, this can be considered as some rule. What is the value of the amplitude at threshold? What is the scattering length? So by traditional subtraction, we typically recover an scattering length. Also, this dispersion relation now has a very correlated relation with the scattering length. That is kind of the answer. If you move the subtraction point to a different point in the energy region, then you will correlate your dispersion relation a lot to that given point. For example, I put it at this threshold, but I could have put it at 0. That is also related to other things. The subthreshold expansion, for example, that is called, and that can be related to KPT. So to kind of perturbation theory. So it's a way, for example, for us to weigh differently the dispersion relation on different regions. So if you're interested about some expansion and you want to look at some observables, you might want to include subtractions there. If you want to look in another region, or for simplicity in this case, we want to put the numbers somewhere else. But at the end of the day, this is all contained within the amplitude. So it's like different observables that we can gather out of the amplitude, but it's not a different amplitude, it's just the same one.
So you can kind of just, if you have the entire amplitude and then you start writing down your dispersion relations to relate the real and imaginary parts, if you piece them together and you don't get the original amplitude, would that tell you that there needs to be a subtraction term somewhere?
It's not exactly the subtraction term,
Okay.
but what that is telling you is exactly what we were discussing before. This is a very good question. What it's telling you is that these two are not compatible, right? This is exactly what you said.
Okay.
If I get the fit to the data, I have my real imaginary parts, then I compare to the real imaginary parts that I get from the integral equation, right? And then they do not match. Is this what we are asking?
Yeah, exactly.
So this means that we are violating cross-check. Because if we were respecting cross-check, then the two of them will be equal. If they are not, then it means that we are not applying the 3 first principles. And so this is what we have to do. We have to make them to be compatible. And you do that by just varying the parameters of the original fit to the data a little bit, so that you recover something that is compatible. So now this real imaginary parts match.
Thank you.
One question for Arkaitz?
Yeah, it seems like everybody wants some rest.
I have one actually.
Yeah.
How can you guarantee that when you build your dispersion relationship, they are model independent and you can just look any model and you are sure that that's going to be your final answer?
Yes. So this is within some bounds.
Okay.
So within some bounds. So if the data is horribly grown, then there is nothing we can do. Okay. But let's say the data is just slightly grown. So then you can see that within those bounds, whatever model you use to describe the data, they will all be slightly different because they have different parameters, different expansions, so they will fit the same data. But they will have some epsilon of difference here and there. If they all fit the data, they cannot be very different, right? But they will be initially, there will be some differences. The idea is that whatever one of those you use, if you impose the dispersion relations, the result at the end of the day is 1 and is unique. So if you start within those bounds, and then you constrain up to full solution where everything is identical, then this is a point, and with some errors when you propagate your errors. But that means that within some bounds, within some spread, you can have like 10 different models describing the same data, and then when you constrain dispersion relations, then 10 of them will converge to the same point. And this is what we call model independent. Okay. Any more questions? I think we are done with these lectures. Hope you guys enjoyed it. I'm going to drop some bibliography today on the Slack channel and some papers that you might find interesting. And I'm going to be around here at JLab. So if you don't find me in this room and you want to talk to me, I'm in the theory center most of the days. And you can also drop me a message on Slack and we can chat. Thank you.